You guys ready, Greg and Cayman?
Oh, yeah.
I'm recording.
All right. So today on the Tendermint Dev session is our first external contribution from Chainsafe on the work they've been doing for the ETH2.0 Light Clients. You guys can start whenever you're ready.
Yeah, cool. I'll kick off just what we're doing, and then Cayman can go into like the research he's been doing. So we're for ETH2.0, we're building the JavaScript, like a TypeScript and assembly script ETH2.0 client with a heavy focus on essentially just trying to build up developer tooling, and also we're trying to lead out a lot of the light client research surrounding ETH2. Because essentially the idea is if we have a fully functional JavaScript client, we can then basically run that client in something like MetaMask, which then omits the need for, and if we have a light client to boot, then we can kind of omit the need for something like, Infura, and kind of trying to further decentralize the ecosystem. So we've been working on that now for closing in on a year. And in the last, I'd say, 3 months, Cayman's done a lot of research in the light clients, and I think that's kind of like an interesting area of topic here because there's a bit of an overlap based on what you guys have been working on. So I think Cayman will kick off a little bit of that, unless there's questions in surrounding kind of like the client itself. Otherwise, we can kind of dive into some of the research stuff.
You can dive in. Usually on this call, silence means go ahead.
Okay. Yeah, so just to echo what Greg's been saying, we've been doing research for a few months, kind of just first getting like comfortable with like the kind of core protocols, at least what has been spec'd, and then prototyping some stuff and seeing where kind of some of the tricky spots may lie. So I guess I can maybe just like start off with what we've been prototyping, or like kind of what kind of concerns we've been thinking about. I'm not sure exactly how the Tendermint Light Client works, but I suspect it's pretty similar to how most light clients work. You kind of have some kind of syncing protocol where you're maintaining and updating some trusted root, some trusted Merkle root. And maybe that's in a block header, maybe you're going header by header, maybe you're skipping forward. Doesn't really matter. It's kind of in detail. It does matter, but it's kind of in detail. And then from there, you once you have a root, you then request some data from some light client server, and they give you back the data that you wanted along with a proof. And in ETH2's case, it's a Merkle proof. I'm sure there's other types of constructions that are going to come out or that are probably out there already. But in ETH2, we're using a simple binary Merkle tree to hash things up. ETH2 has this kind of custom serialization spec or Merkleization spec. It's called simple serialize, SSZ, SSZ, if you will. And it defines kind of different primitive types that can be serialized, Booleans, integers of various lengths, or unsigned integers of various lengths, and arrays, lists, and kind of heterogeneous structures like some kind of object. And it defines a standardized way of like Merkleizing whatever object it is into a single root. And by having a nice standard for that, it makes it really a lot easier to understand or to map that to what a valid proof would look like, or map that to what the kind of the Merkle tree behind the scenes looks like. And so that's really useful for light clients because you're going to be requesting proofs, and you're gonna like the more information you know about what data you're getting back, it might change how you're representing these proofs. So in prototyping this proof stuff, we started with just kind of extending our simple serialized library to include the ability to create arbitrary Merkle proofs. And in fact, ETH2 has this kind of concept of a multi-Merkle proof. And it's not really that complicated. It's just a Merkle, like a normal Merkle proof where you have a leaf and then these sibling chunks along that kind of go all the way up to towards the root. And you use those to like verify the proof. I mean, that is the proof. Instead of having just one leaf and then this like chain up to the root, you can have multiple leaves, and then you will share whichever intermediate nodes can be shared. And so you're kind of combining multiple proofs into one, and it's just a way of like saving some amount of data, some amount of bandwidth. And it works really well when like thinking about the data that you're getting back as to some object. So you can say like, you know, if you had an object that had like field A, B, and C, you could say, oh, give me field A and B. And then you could like turn that into a proof, and it'll give you back just A and B and whatever's needed to like recalculate the root. And so the way we've been thinking about this is as a kind of on a developer side, or like on a what kind of interface we've been thinking about is we'll have some kind of, for generating a proof, we'll have some object that we know it's an SSZ object, so it has some very specific fields, and we know kind of what that schema looks like. And we can say, make a proof for these different paths. And a path is kind of tells you a very specific place in the object. So maybe the object has like sub-objects. You can like, you know, go as deep as you need. And then this, you know, the code that we've been prototyping will create the right proof for you. So where there's some interesting, or where there's some like interesting play is we've kind of been realizing that there's more than one proof backing or proof representation. So there's more than one way to like represent this proof with data. You know, you can use kind of we were calling the classic kind of representation, which is you have an array of leaves, and then you have an array of sister nodes or sister chunks. And that's kind of like the most basic. Alternatively, you can do things where you're embedding the structure of the tree a little bit more in with the proof. So when you have just like an array of leaves and an array of sisters, you're not actually encoding which places in the tree the leaves correspond to. And so you actually need that as a user of the proof in order to be able to recreate the root. So like whether or not you know which indices, if you will, which places in the tree you're looking for or that you have access to, whether or not you know will depend on, will change what kinds of representations of the proof can be available to you. So in most cases, you know, like we know when we're requesting a proof exactly what data we're going to be getting back, like what place in the tree that is. If we're making some really exotic call or some kind of really exotic request, that goes really deep into some tree, like it might be kind of unknown where exactly that data lives or what that tree looks like. And so if we requested a proof, we would probably need to request a proof in a way that also embedded the structure of the tree or somehow encoded the places in the tree that the data that we're getting corresponds to. otherwise that we won't have enough information to recreate the root, like, you know, like here's kind of what you're wanting to do with the proof. You're not going to be able to verify.
Yeah, so I'm not sure I totally understand. So uh, is the structure of the tree changing or something? Like why do you have to know more about the structure of the tree depending on the?
So like, let's go to a case in ETH2. It's kind of changed since we've been thinking about it, but I think that there'll probably be cases where a similar kind of thing might happen. So in ETH2, we had the idea of crosslinks, and a crosslink basically still has a root to a variable number of shard blocks inside of it. And like this data structure, this crosslink, it has the root, it has the start epoch and the end epoch of what that root corresponds to. So let's say I want to get like the quote unquote latest shard block data. If I wanted to get that in one pass as like a proof, or sorry, maybe not the latest. So I want to get it at a certain epoch that's like very fresh, because the crosslink is a variable number of epochs wide, or because that root corresponds to a variable number of epochs. I don't know exactly, like if I were to imagine that root it's the root of a tree, and then, you know, down the leaves of that tree is the actual data that I'm looking for. Mm-hmm. I'm not sure exactly what path I need to trace to get to the data I'm looking for, because it's a variable number. It could be, you know, only
sure, but isn't that only a concern for the on the server side? Like once the server serves up a proof, doesn't the proof make clear what the path is? So you said it's a binary tree, right?
Yeah, not necessarily. So you don't always know the play. Usually you do, but then there's certain cases where, like, if you want to make a really long proof and there's something that's variable.
What do you mean a really long proof?
So like in ETH, the other kind of thing that we're doing is we have.
Oh wait, sorry. Does this go back to? I mean, I think at the beginning you were talking about being able to serve multiple proofs in a single response and deduplicating shared shared proof nodes, shared ants.
Yeah.
So is that why you won't know the structure necessarily, because you won't know where an ant actually is in the tree?
No, it's more about like things that have like variable width, or things that where maybe the index is changing on every time, every like click or so. Kind of things like this crosslink scenario where you're wanting to get a specific point in the crosslink, but you don't know where it is until you, like, another way of doing it where you do know the structure ahead of time is you could first request the start epoch and the end epoch within a crosslink. Now that you know the width of the crosslink, now you know kind of what that structure of the root looks like.
And what is a crosslink with respect to a Merkle tree?
A crosslink is just a data structure that has a variable width. It has a root that corresponds to a variable width of like some array, some variable length of data. Mm-hmm. And the data is the leaves, and you're trying to, like, you know, get a proof for some part of that.
How is that different from any other Merkle tree storing state with a variable number of leaves?
Because of just how you'd expect a user to request that data. The underlying data represents data at some epoch in time, mm-hmm. and a user might request data for a specific epoch, or like for like the latest epoch -1 or something, and there may be a situation where they're wanting you need to know the start or the end epoch before you actually reach into the tree. Mm. And so depending on how you've like defined your data structures in your chain, it kind of limits you or doesn't limit you to how deep of a proof you could make at once. You can always make proofs with multiple in multiple steps, where you get enough data to figure out what the tree would look like further down, and then you request more, and you request more, and you get further and further down into the part of the data that you actually want. Or you can request it all at once and get a proof that encodes the places in the tree that you're getting back, or encodes the structure of the tree, which is just kind of another way of looking at it.
Okay, I'm not sure I'm gonna improve my understanding at this point without pictures, so maybe we
Yes.
should move on.
So sorry, I didn't bring any good visuals.
Right. Are there diagrams of all this stuff? I mean, online or?
There are diagrams. I don't know that they're recent.
Your slides from DevCon, huh?
Slides from DevCon would probably be the best bet.
Yeah, that's probably a good idea. Also, you mentioned this SSZ thing. Is there a rationale document for why another serialization algorithm was created?
I bet you there's like a few sentences. No, I think the reason was for like easy Merkleization.
What does that mean?
So like,
I think you might have said you Merkleize the objects themselves. Is that right?
Yeah.
Oh.
It's just a way of like, you have some simple object. You have some like objects with like pretty basic types in there, nothing exotic. No like instances of classes that you need to like hold on to. And then you can like turn that into, you can Merkleize that really easily.
But why do you, what's the use case for Merkle? Like, isn't a light client going to typically request the whole object, or is it really a use case?
Not necessarily, because the entire, in ETH2, like the entire chain is Merkleizable, and we have like roots within other data structures that can be expanded into, like every object that's on the chain is simple serializable, uses the same format, and so we can like make proofs that dig into a data structure that has a root, and then imagine that root is the full object, dig into that data structure and like navigate through the sea of roots, or navigate deeper and deeper root by root, and it's all using this like standard format.
I see.
I don't know if it needs to be so fancy, like, but that's kind of the idea.
Yeah. Yeah. So I mean, for instance, just a comparable, like we have for the Tendermint header. So we're basically using, we're also guilty of bad design decisions when it comes to serialization. I think that's part of it's maybe an initiation, right? When you get into the blockchain space, is that you have to deal with someone's bad serialization algorithm. But I guess it remains to be seen if SSC is how that's going to work out. But so we have this amino thing, which we're trying desperately to just bring down to protobuf 3. So hopefully soon it will just be protobuf 3, but we're not quite there yet. But anyway, so our header, for instance, is a header. The header actually is purely protobuf 3, if I'm not mistaken, which is nice. But we also Merkleize the header. So we just take the individual fields, encode those as they would be as protobuf types, and then build like a simple Merkle tree out of that. And so the hash of the header is actually a Merkle tree of the fields, and then a light client could just verify if need be. But I mean, the header is so small. I mean, our header is actually kind of big, but regardless, like by the time you're verifying a proof of it, you might as well have just downloaded the whole thing. And so I guess I'll have to understand more of the system to see where the value of Merkleized independent objects really comes in with respect to the light client, like where where you don't want to actually expand the object. Because I mean, unless you have an object with a huge number of fields, if you're dealing with 32-byte hashes, you know, where does it really make sense to not download the whole object and to only look at the root?
Yeah. So like one example of that might be like the whole like beacon state.
Okay.
So like we have a beacon block, and the beacon block has a state root, and the state root is this Merkle root of the beacon state, and the beacon state has the entire validator set in it. You know, all of the validator statuses and the balances and all that, and so like, I don't know, this is a really kind of a very crafted example, but if you wanted to like, you know, you don't want to you never really want the whole beacon state as a light client. You probably want like some reference within the beacon state only. So like one field, maybe like the cross link. So like the shard data is like linked through the beacon state, or you'd want some only small fraction where you want only one field.
Okay.
I mean, naively put, I mean, like you could think of it, let's say you've got some app running in the browser that just shows you statistics of like the latest block header, right? You don't care about all the other data. You can just request that one piece.
Right.
Request just the block header, or you could request, and like versus doing it through like RPC, right? So, I mean, again, crafted, but
okay.
Or if like, let's say you only want it, like you want to get your DAI balance, right? You want to get like some specific token balance and display that one specific token balance. Like, you'd have to go pretty deep just to even try and find that. So the ability to just like extract just one little piece of it's quite helpful.
That maybe brings us to a good segue. Are you guys doing anything with WASM by any chance?
Not per se with respect to the Light client. I mean, there is a team that's starting to work on WASM integration into the Cosmos SDK, but it's not like, you know, an inherent part of any of the protocols yet.
Okay. Because this is another thing we're looking at Light client wise is like when you have your like blockchain kind of in WASM, when you're dealing with like this like stateless client, you kind of need it's almost separate infrastructure that you need for Light clients, because you don't know the proof. You don't necessarily know the proof format ahead of time. You probably do, but if you're in some like a case like where it's more permissionless, like I get the sense that in Cosmos anyone could spin up their WASM, their own like blockchain that has their own rules. You don't, as a Light client developer, you don't really want to have to like rewrite proof verification for each different accumulator type that someone might come up with. Maybe there's only a handful, so maybe it's not that big of a deal, but we're kind of realizing that, I don't know, it's kind of just a separate, like, at least in the Ethereum ecosystem, like, not only is the way that you probably think about getting these proofs different, but even the actors that hold the data are completely different. And so, like, who you're requesting the data from, like, how you're requesting the data, that's all very different once you go into this WASM world. And maybe that's because of the design decisions that Ethereum has, and maybe some of that's just having to do with how the rules are very different. Is there anything specifically that I called out that it's more interesting, or I can go into a little more detail on?
Well, so I mean, we've spent a ton of time on the Light client for Tendermint without even thinking about the application. So forget about, like, you know, the state queries, just looking at basically following the consensus. And the main challenge for us there was the fact that the validator set can change arbitrarily with every height. But I guess that's not really a problem in ETH2, or maybe you can give us a brief overview of how validator set changes in ETH2 happen, how that affects the light client, and how you think about like detecting forks, like fork accountability and fork detection and so on.
Yeah, so at a high level, the way it works is the way we kind of get around this validator set changing every single time is we've designed the shard blocks to have a more persistent committee, a committee that won't change except every I think 27 hours is like what the constant is set to right now. And so the idea is for syncing or staying up with consensus as a light client. At minimum, you could just sync every persistent committee chain. You can look at just the shard block. Don't track the main beacon chain. Just track the shard chain, a single random shard chain, and basically every 27 hours get a few pieces of data, get the latest shard block that's signed off by one of the proposers, get the change in the persistent committee, so that you can update your committee, this like small subset of validators.
How do you verify the change in the committee? The committee, and the committee is like the validators on a particular shard. Is that right?
Yeah. Sorry, yeah.
And how do you verify the change?
Let's see. I'm just going to go back to the specs real quick so that I don't mess this up. Okay, so so the way actually it works is there's this underlying committee that changes every 27 hours, but actually what's the subset of validators that's used to vote on shard blocks is actually a blending of the current committee and the previous committee, and so when you get a new committee, you're still able to be using some of the it's kind of a blending, and so
the decision for the new committee comes from the beacon chain, right?
Yes.
And we're talking about a light client that's not verifying the beacon chain.
That's right.
And so what'll happen is on the shard, you'll end up with a new validator set that's a mix of the old validator set and the new validator set from the beacon chain.
Yeah.
And how is that mix determined? Or is it everyone?
So the mix is the algorithm isn't really shared with the light client. So the light client gets a new beacon block header, and the beacon block header is it's verified against the new shard block header that it gets, and so you're like trusting the shard block security, I guess, to give you the right beacon block header, and let's see. Sorry, can you repeat the question?
Yeah, well, sorry, was someone else trying to say something?
Yeah, I was asking if the spec you're looking at, you're checking, is it public and it's in a link?
Yeah.
For our future reference.
Cool, thanks. I'm asking how so the beacon chain determines a new validator set every 27 hours. Is that right?
Yeah, a new, yeah, exactly.
For each shard.
For each shard, that's right.
And then so the shard, like, so say we're on, I don't know, call it shard A, and shard A sees, oh, I have validator set A currently, and now the beacon chain's telling me I need to move to validator set B. And so then you're saying that first it changes to a validator set that's a mix of both. Is it just like you add both validator sets together and that's the new validator set for a bit, or how does that like validator set transition on the shard actually start to execute?
So there's an algorithm, and it just uses some like randomness to like kind of slowly move from one to the other. But I think the key piece that we were looking for was that we store these persistent committees in the beacon chain, and we're given a proof from the beacon chain to the committee to prove that the new committee is legit.
Well, we're not, but I thought we were talking about a light client that's not following the beacon chain, or do they have to?
It's not following it's not, so it is following the beacon chain, but only through a shard chain. And the reason is so that they only are tracking persistent committees and then like relying on the beacon chain to verify the persistent committee, but they're verifying the beacon chain through the shard chain data that they get. So a shard block has a route to a beacon block inside of it. And we're kind of navigating that way to get a proof for that.
Okay. It sounds a little bit backward, right?
I mean, if you can trust the security of Casper, of like getting this, if you can trust the security of this committee and you get it, it's being shuffled, then I would I'd expect that it would work. It's a little strange because you're like only looking at this one committee, or it's only this one shard and not the full validator set. But it definitely makes like a light client a lot lighter, right? Because we're only downloading, like, I don't know, like 7 kilobytes to get this committee every 27 hours.
And how big are these shard validator sets?
I want to say on the order of like 128 validators.
And on the beacon chain, is there a size?
Or
is it unlimited?
Yeah, it's unlimited, but I mean it's practically limited to like 4 million, but it's probably going to be less than that.
4 million, huh?
Yeah.
Okay.
It's limited by the number of ETH in existence, but I would say we're targeting tens of thousands.
Is there tens of thousands of validators participating in Casper on the beacon chain?
Yeah.
Wow. Okay. That's ambitious.
Yeah, I think the idea is to start with 2 million Ether locked up. So that's 2 million.
Over 32 is the minimum?
About 32, yeah. So that's 62,500.
Right. But probably a lot of people will lock up more than 32. So
yeah,
get there with like 1,000 people locking up a few thousand Ether or something.
Exactly. Yeah.
Okay. Interesting. Sounds like there's a lot to digest in here. And so how do you do skipping? So when a light client wants to not verify every header.
Yeah. So we're only verifying. You could potentially only verify a header every 27 hours.
Because the validator set doesn't change within that.
Yeah. Right.
And how long are the validators bonded for?
Validators
are slashable.
They're slashable for a variable amount of time, somewhere between, I want to say, like 48 hours and like weeks, depending on how many people are trying to exit at that time.
How many validators are trying to exit?
Yeah. So there's a queue, and then it gets filled up, and then it takes a long time.
But how do you communicate that variable timing to the light client? Like, how does a client know how long it can go? It has to come on every 27 hours anyway, if it wants to stay synced.
Yeah.
So then why do you need a longer unbonding period if it has to be on? Oh, for the beacon chain. I guess there's unbonding. There's a light client. There's a difference between a light client only following a shard and a light client following the beacon chain. If you're only following the shard, you have no choice but to come on every 27 hours. Otherwise, you're going to have to rely back on the security of the beacon chain. And so on the beacon chain, you have some longer unbonding period on the order of weeks, I guess. And then a light client that goes off for, I don't know, a few days would then have to sync with the beacon chain to be able to get back onto a shard. Is that roughly right? Or?
I think you'd still, even if you went offline for a few days or a few weeks, you'd still be, I mean, you're relying on like the data being available, but I think you'd still be able to sync just 27 in leaps of 27 hours.
But if those validators are no longer slashable.
Yeah, but the data is all still, I mean, assuming the data is all still there, it's all there in a Merkleized form, somewhere in the ether.
But if those validators aren't slashable, they could be sending you data that's just patently false that causes you to think that the validator set changed in a way where it didn't.
Well, I think that's only if you've gone out of the weak subjectivity period. So like, if you're starting from a place, well, if you're starting from a place where like you know that it's right, then you're always updating some amount of the validators where you trust other amount of the validators. So you can like build off the trust that you've started with to like get you to the next step. You can't skip a 27-hour period for sure, but you can, if the data is there to be requested, it can't be forged. So you're like,
you said that the unbonding period, the slashable period is variable, and that sometimes it's as low as 48 hours. Oh, but it depends on, I mean, if all the validators from a shard manage to exit in a short period of time, does that necessarily mean that their unbonding periods are going to be longer because they all exited at the same time?
So is I feel like it is, but I feel so the worry is that of a validator who's signed a block, the block that you would be using as a light client to update the chain, it's 27 hours. The worry is that they've double signed. They've signed a malicious block then. So if they did that, if they only served it to you, that's an issue. If they were to broadcast that block, they would be slashed.
No, but they've eclipsed you. They're only serving it to you. They're no longer bonded. They're no longer slashable. I mean, if they're no longer slashable, obviously the client needs to be able to know somehow that they're no longer slashable so that it can ignore, so that it either needs to go back to the beacon chain or reset its state subjectively. But this variable unbonding period thing sounds very, very complex, especially in the sharded environment. I mean, I don't know nearly enough about the way this protocol is set up, to be honest. So there's, that's on me, but yeah.
I guess I need to think about that a little bit. But it's a good thought.
Okay. And how do validator set changes on the beacon chain happen? Are those just fully dynamic, or?
There is an activation period. So there's a few different ways you can become active. There's the ETH. So initially, all of the ETH is on the ETH1 chain. So we're starting up a deposit contract. It's an enshrined contract on the ETH1 chain that ETH2 is listening to. And you deposit 32 Ether and some data with your credentials on the ETH1 chain. ETH2 is listening to that. You get put into a queue, and eventually you get turned on, or your status gets to turn to, like, you know, you're validating and you have responsibilities. And then you can voluntarily leave, or you can be slashed and like kicked. Or you can just, if you're inactive, then eventually you'll be kicked as well.
Right.
So I believe the only way is through the deposit contract right now.
But once you're moved over, can you not buy ETH2 directly and stake it? Like, you can only.
No. So
What?
in the first few, I mean, at least not in the first kind of phase of
Okay.
things.
I see.
So there's kind of an issue that we're trying to get around by kind of making things a little more frozen, and that is trying to avoid having ETH1 and ETH2 traded independently. Because if they're traded independently, then there's some questions around whether or not they're separate assets. And then there's like tax implications to that.
Oh my God.
And they're supposed to be, I mean, they're meant to be the same asset. It's just a slow migration process. And so until or unless there's a two-way bridge from ETH1 to ETH2, it'll probably be more like frozen like that.
So it'll be non-transferable.
Yeah.
Until there's a bridge back, or until enough moves over, or what?
Or until ETH1 gets moved into ETH2. But probably there'd be a bridge, just because it's gonna be a while before ETH1 gets rolled in.
But basically, until then, ETH2 is not really usable. Like, no one can do a smart contract or anything.
No. So like the launch that we're going to be having in Q1 it's a bare Casper chain. So like that's kind of all it does, is just like
Q1. That's the target.
Yeah.
ETH2 is launching in 6 months, 4 months.
Yes. Yeah.
Wow.
I mean, granted, it's just a Casper chain, right? So like, I mean, there's a lot of moving parts, but it doesn't do smart contracts. It doesn't do all the fancy stuff. Like, it's not really meant for users. It's just meant for stakers, I guess.
Yeah.
And,
it's like the Cosmos Hub.
Yeah. So it's a good start. It's a good foundation, but, and you're going to build off of that, obviously, but the smart contracts don't come until later. And
so these implementations of Casper are working and tested, and what's the on large validator sets, or what's kind of the state of the software implementations?
So there's 6 different teams that are building 6 different implementations. And we've come to a few months ago, maybe, 2 months ago, we met up in Northern Ontario and for a week, and got everyone working on very small validator sets with a minimal kind of network configuration.
Right.
So we have at least some confidence that the basic system works. There are a few kind of front runner clients that are much more productionized and optimized. So I'd say our client Lodestar is a little we're still working to make it work with large validator sets, but like say like Lighthouse and Prism and Nimbus, they've been working, they're writing their client in like a good systems language and like been going for a lot longer. And so they're working with, very large validator sets, and they're able to process blocks in, sub 200 milliseconds. And like, they're doing like really, really well. And so it does seem like we're on for Q1.
That's awesome. And are they all staged for like third-party security audits, or how is that being coordinated or handled?
So it's being handled independently by each team. So these 6 different teams are run by 6 different companies, and they have very different priorities and skill sets and all that. I know for sure, I have heard for sure that there's going to be a security audit for Lighthouse and for Prism, and I suspect that any like self-respecting client would be getting a security audit, or I wouldn't be trusting it really. So I know for sure that some are happening, and hopefully more eventually.
Very cool. Great. Well, good luck, guys. It's awesome. Cool.
Yeah, feel free to ping me, on Twitter or wherever, or GitHub. And if you have any more questions.
Sure. Yeah, I think we need to look a bit more at the spec, both for ETH2 itself and for the Light client, to be able to ask more intelligent questions. Was someone else about to say something?
Slides,
oh, Greg.
Yeah, in the chat. So his slides that he had from DevCon on ETH2.
Oh, great.
So they're pretty interactive, and they kind of show the structures and stuff quite nicely. So it might help if you do end up reading the Light client spec, it might help kind of understanding what's going on.
Okay, great.
So, and it's a HackMD. If you look at the kind of like the text version, there's a bunch of speaker notes, and that might be more helpful than just like the slides are. There's only so much on the slides, and it's pretty high level, so it's
Yeah.
Kind of a side question. How did you guys decide on TypeScript?
Greg?
Yeah. Back in like a year ago, June, we were kind of looking at all the clients, and and back then we're like, oh, let's do it in Go. Nah, there was already one, and then even like the Geth team was like thinking about was doing like POCs. So we were like, all right, we'll scrap that. And we basically went down the list of all the languages that were being written in, and just said, well, fuck, I guess JavaScript's available. And then we're like, well, let's do TypeScript, so at least it's like legible code. And one thing led to another. We realized there's like an actual opportunity here to a lot of the dev tooling needs to be replaced. Like the Ganache and Truffle suites need to be like fully gutted for an ETH2 implementation. So we kind of said, let's just like run with this, see if we can like take over like the dev tooling side for ETH2, and kind of doing that, I guess, right now. It's a little bit slow, but that's how it came to be. It's not my first choice. It's frustrating, which is blowing my mind. We're not like stupidly slow. We're just like not efficient, I guess. Right? Not yet. But assembly script's really helping, right? So that's like gave us a huge speed up in SHA. We wrote our own SHA in assembly script, SHA-256, and based on like compiling down like Rust implementations, C implementations, the native C bindings, like ours is more performant than all of them.
Wow.
And we beat the C bindings, which are the fastest, by I think 1.3 or 1.4x. So assembly script's got promise. So that's helping us like speed things up. We're gonna like put like our state transition probably eventually in assembly script, and just get a lot of WASM in there to make it work.
Cool.
Yeah.
Okay, so that compiles TypeScript to WASM.
Yeah. So it's like a superset of TypeScript, but it's like pretty strict, and it's kind of like unsafe mode, I guess. Or, well, no, it's the same way how like Rust, like if you go in unsafe mode, you're probably not going to be able to compile down to WASM. You know, there's like a super safe mode of like TypeScript they're using. Well, they're just isolating certain functionality. And that's how it's working.
Right.
Yeah.
Cool. Have you guys looked at any of Agoric's work on more secure JavaScript?
I chatted with the MetaMask team a bit about that at DevCon because
Yeah.
I've been following it. And because I think they're using it actually in their new plugin system.
Yeah.
It's pretty cool. Pretty cool. Although I think it still needs a little bit more time, right, before it's like actually verified and stuff.
Yeah, it might be. Yeah.
Properly audited, or I don't think.
I'm not sure. Yeah.
But it looks promising.
Cool.
Yeah.
Okay. Well, thanks, guys. I don't know. Are there anyone else have questions or?
No questions from me, but I just wanted to say thanks for taking the time to share with all of us. And I am not very familiar with ETH2, so this has given me a lot of leads to follow up on and a lot of learning to do. So thank you for that.
Yeah, no problem.
Cool. All right. Thanks, guys. I guess that's it for today. I'm going to kill the recording.